So we are going to go through the solutions for this Chapter 10 activity. What we were looking at is in Unit 4, gases, the various ways that we deal with gases, and I would just like to do a few sample problems so you have a chance to actually review the content. So question 1 says calcium carbonate, CaCO3, decomposes upon heating to give calcium oxide and carbon dioxide. A sample of CaCO3 is decomposed and the carbon dioxide is collected in a 250 milliliter flask. After the decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. How many moles of CO2 were generated? So first thing we're going to do is we're just going to write out what we believe to be happening. Calcium oxide, which is a solid, plus CO2 gas. Give it a quick look, and it looks like we are balanced. Next up, we know that the ideal gas equation is PV equals nRT. We have pressure in atmosphere times volume in liters is equal to the number of moles times the ideal gas constant 0.08206 liter atmospheres per mole Kelvin, and temperature in Kelvin. So it wants to know how many moles of CO2 are we actually producing. That means we want this. So we rearrange our equation to N equals PV over RT. So let's just double check our conversions. We need the volume needs to be in liters. So we'll turn milliliters to liters. The pressure is in atmosphere, so that's okay. The temperature is in degrees Celsius, so we've got to convert that. So 31 plus 273.15 K is equal to 304 K. So as we go through this exercise, what we want to make sure is that we are paying attention to the units. So N equals 1.3 atmospheres times 0.250 liters divided by 0.08206 liter atmospheres mole Kelvin times 304 Kelvin. Kelvin cancels with Kelvin, liters cancels with liters, atmosphere cancels with atmospheres, leaving me just with the unit in moles. N equals 0.013 moles of CO2. And then of course we can go to grams of CO2 or from here. So question 2. The gas pressure in an ideal, assuming an ideal gas, in an aerosol can is 1.5 atmospheres at 25 degrees Celsius. Assuming that the gas inside obeys the ideal gas law, which is what we just said, what would the pressure be if it was heated to 450 degrees Celsius? So we're just going to apply, Charles' law here. So Charles' law is temperature 1 over pressure 1 is equal to some constant value, which means that it's going to be equal to temperature 2 over pressure 2. You can use the ideal gas equation, and with the number of moles, the volume, and of course the gas constant being constant, they will cancel each other out, and they'll leave you with this equation, which is ultimately where we are getting it. So we're just going to substitute some values in. 298 Kelvin over 1.5 atmospheres equals 723 Kelvin over pressure 2. That's what we're trying to find. Pressure 2 is equal to 3.64 atmospheres. We're going to deal with significant figures. Is 3.6 atmospheres. Question 3. An inflated balloon has a volume of 6 liters at sea level, which we assume would be 1 atmosphere, and it is allowed to ascend at an altitude until the pressure is 0.45 atmospheres. During the ascent, the temperature of the gas falls from 22 degrees Celsius to minus 21 degrees Celsius. Calculate the volume of the balloon at its final altitude. So let's actually look at where we're going to get this equation, and then we can kind of use this equation as we see fit. So PV equals nRT. We know that in the balloon the number of moles are going to be constant, so that's always going to be constant. Of course, R is going to be constant. We know that the temperature is changing. We know that the temperature is changing. We know that the pressure is changing, and of course, we can expect the volume to change. So we are going to actually give these variables pressure 1, volume 1, and temperature 1. And once it's ascendant, we're just going to give it the variable 2. But you'll notice that N and R don't have variables or subscripts because they are the same for both cases. So let's put all of the subscripted ones on one side and all the ones that aren't on the other. So P1 V1 over T1 is equal to NR. P2 V2 over T2 is equal to N over R. Since these are equal, I can say P1 V1 over T1 is equal to P2 V2 over T2. So now I can just plug values in. We'll assume this is at sea level and this is as it rises in the atmosphere. So pressure 1 is 1 atmosphere. The balloon is 6 liters there, and the temperature is 295 Kelvin. Of course, converting from 22 degrees Celsius. And that's going to equal 0.45 atmospheres to whatever volume, which of course is what we're trying to find. And we know the temperature at that height is 252 Kelvin, or minus 21 degrees Celsius. So 1 times 6 divided by 295 times 252 divided by 0.45, and we get 11.4 liters is equal to V2. Let's check significant figures. We only have 2, so I should probably just leave it at just 11. So we continue moving on. So question 4 says, what is the density of carbon tetrachloride vapor at 714 torr? There's a lot of different things we can do here. I can't really deal with torr. There is an R value that allows you to. I prefer not to use it. So we know the density of a gas is equal to PM over RT. That comes directly out of our note. We can't, because I'm just going to use 0.08206 for R, I'm going to convert pressure, and I'm going to do it right in the equation. So 714 torr over 760 torr. Carbon tetrachloride, I need the molar mass of it. So tetrachloride is 70.9 times 2. So 141. 153.8. And that's, of course, grams per mole. Ignore that arrow. The gas constant. And the temperature is 125. So that's 398 Kelvin. We throw it together. I get 144.5 grams in 32.659 liters is 4.42 grams per liter. That would be the density of carbon tetrachloride. So for number 5, we've done a question very similar to this in class. It says a series of measurements are made to determine the molar mass of an unknown gas. First, a large flask is evacuated and its weight is found to be 134.567, or at least its mass was. So mass, let's call it mass 1, is 134.567 grams. It's filled with gas to a pressure of, so let's put pressure is equal to 735 torr. The temperature, 31 is not useful, so let's turn it to Kelvin. 304 Kelvin. Let's call it mass 2 is equal to 137.456. Alright, so we know that the mass of the gas is being included here. When the mass, we then take the flask and fill it with water to determine the volume of the container, and we weigh it. And of course we assume that the density is 0.997 grams per mil at this temperature. And the density of water is temperature dependent, but you can look it up pretty much if you search it on the internet or use a reference book, you'll find the density. So the first thing we are probably going to need to worry about is just what exact equation we're going to use. We have one for this exact case, and it says the molar mass, the density one. Molar mass is equal to the density of the gas times the ideal gas constant times the absolute temperature divided by the pressure. So I have R, I have T, and I have the pressure. I'm going to want to be in atmospheres. So we're going to convert this to atmospheres by dividing by 760. So that's equal to 0.967 ATM. Just a quick calculation to make that conversion. So what we have left to do is to get the density. So density is equal to the mass, which is the difference of these two. So M2 minus M1 divided by the volume. So we need to get the volume of the container. And how we're going to get the volume of the container, we did this again in class, is we're going to take the mass of the container full of water, take away the mass of the container empty, and we are going to divide that answer . So my grams are going to cancel, leaving me with milliliters, and that's going to hopefully give me the right answer. So as we go through this, 106.9, take away 134.567 equals try that again. So equals 936.14 milliliters. We can't deal with anything in milliliters, so we know that that's 0.936 liters. And that's our volume. So density is equal to 2.889 grams over 0.936 liters. So now I have grams per liter, I have my density, so I've got it all now. So density, ideal gas constant, temperature, and the pressure. So the molar mass of the gas is 79.71 grams per mole. So question 6. The safety bags in automobiles are inflated by nitrogen gas generated by the rapid decomposition of sodium azide, NaN3. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.15 atmospheres and at a temperature of 26 degrees Celsius, how many grams of NaN3 must be decomposed? So PV and RT. Well, R is easy enough. Liters, atmospheres, mole, Kelvin. We know the pressure wants to be 1.15 atmospheres. We know the volume is going to be 36 liters. And we know the temperature is 26 degrees Celsius. So 26 plus 273 gives me 299 Kelvin. So the question becomes, what is N? So PV equals nRT. N equals PV over RT. It's 1.15 atmospheres by 36 liters. 0.08206 liters atmospheres, mole Kelvin. 299 Kelvin. So 1.15 times 36 divided by is 1.687 moles. The question wants it in grams. So 1.687 moles of N2. Again, remember this is N2 times 2 moles of sodium azide for every 3 moles of nitrogen. Times molar mass of sodium azide, so 14 times 3 nitrogens, plus 23 is 65. So 1.687 times 2 divided by 3 times 65 grams per mole is 73.1 grams of sodium azide. So question 7. A gaseous mixture made of 6 grams of oxygen and 9 grams of methane is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas, and what is the total pressure of the vessel? So let's first convert to moles. We can't do anything in grams. One mole of oxygen is equal to 32 grams of oxygen. 1 mole of methane is equal to 16.04 grams of methane. So this is 0.1875 moles of O2. and this is 0.561 moles of CH4. The total amount of moles of this is 0.749 moles. Again, the pressure of a gas is controlled by the number of moles. It doesn't really matter what they are. So PV equals nRT. Let's just rearrange it to get P by itself. .273. We're in absolute values or temperatures, and the volume is 15 liters. So the total pressure is 0.841 atmospheres. We can then determine the partial pressure by doing something called mole percent. So mole percent is simply the, or mole fraction. XO2 stands for the mole fraction of O2, and it's the number of moles of O2 divided by the total number of moles. So that's going to be equal to 0.1875 divided by 0.749. So 0.1875 divided by 0.749 equals 0.25. If the mole fraction of O2 is 0.25, then the mole fraction of methane must be equal to 0.75. So all you have to do now to get the partial pressure of each gas is multiply their mole fraction by the total pressure. So the pressure of O2 will be equal to 0.280 atmospheres, and the pressure of methane will be equal to 0.841 atmospheres. Which means that this is the pressure of this value, and this should be 1.12 atmospheres, because these have to add up to the total pressure. We just check our answer here. 0.749 times 0.08206 times 273 divided by 15. Yeah, the answer is 1.12 for this calculation. That was just a little error. Question 8. Study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole percent of CO2, 18 mole percent of O2, and 80.5 mole percent of argon. Calculate the partial pressure of O2 in the mixture of the total. So remember that Dalton's law of partial pressures says that the total pressure is equal to the pressure of the sum of the pressure of the components. So CO2 plus the pressure of O2 plus the pressure of argon. And that's simply Dalton's law of partial pressures. We also know that the pressure of CO2 is equal to the mole fraction of CO2 times the total pressure. So the pressure of CO2 would therefore be equal to 0.015, because it's percent. It's 1.5%. So converted to a decimal, that's what we would see. Times 700 745 torr would be the pressure of the atmosphere. So the pressure of CO2 0.015 times 745 equals 11.18 torr. And we can repeat this for every gas. So for part A, it says calculate the partial pressure of oxygen. Well, the partial pressure of oxygen is equal to the mole fraction of oxygen times the total pressure is equal. So again, that's 18% turned into a decimal times 745 torr. And that means this is equal to 134 torr, and that's the answer for part A. Part B says if this atmosphere is to be held in a 121 liter space at 295, how many moles of oxygen are needed? So for part B, we simply are going to use the ideal gas equation. Again, we got to be in atmosphere, so 134 over 760 torr divided by torr per atmosphere, just to make the units work out for us. The volume is 121 liters. The ideal gas constant and 295 Kelvin. That's equal to 0.088 mole of oxygen. And it asks for moles, so we are good. That's our answer. So number 9, it says a sample of potassium chlorate is partially decomposed, producing oxygen gas and collected over water. The volume of gas collected is 0.250 liters at 26 degrees Celsius and 765 torr of total pressure. How many moles of oxygen are collected? So that's the first one. A. As soon as it asks me for moles, I'm going to go to the ideal gas equation. It's not really giving me a vapor pressure of water, so I'm not going to worry about subtracting the partial pressure of water away from this. If they wanted me to do that, they probably should have included it in the question. I'm not going to go look that up. We're going to assume that it's insignificant here. So 765 torr over 760 torr per atmosphere. The volume is 0.250 liters, 0.08206, and it's 26 degrees Celsius, so that's 299 Kelvin, just adding 273 to it. That tells me 0.010 moles of oxygen are collected. For part B, it's not actually a gas equation because I have the amount of oxygen that is produced, so I'm just going to convert that back to potassium chlorate. So 0.010 moles of oxygen. It's 2 moles of the potassium chlorate for every 3 moles of oxygen consumed. So that gets me to potassium chlorate. The molar mass of potassium chlorate, just looking it up. And that would be 0.817 grams. Will produce a quarter of a liter of oxygen. So question 10 deals with Graham's law. And Graham's law is described here. It simply says that the rate of the unknown gas over the rate of the known gas, in this case oxygen, is proportional to the root of the quotient of their molar masses. So it's a really neat relationship, and we talked about it in class as the rate that a balloon would deflate with different gases, and the smaller the gas, the quicker the balloon would deflate, which is why helium balloons need to be different than regular air balloons, because helium is so much smaller than air, which is mostly nitrogen and oxygen. So for this equation, what we're going to do is we're just going to use this. So it says they're homonuclear, so meaning the same molecule, and they're diatomic. So that limits us to what these possibly could be. It would be hydrogen, nitrogen, oxygen, fluorine, bromine, iodine, those types of gases, the diatomics. So it says 0.355. So the unknown gas is going to be 0.355 times. So that means that this whole side of the equation is 0.355 over 1, essentially. It's just over a third of what oxygen is. So that's why I'm doing that. I'm making oxygen 1 and then just making the other 1.355. We know what oxygen is. So what I'm going to do is I'm going to write 0.355 equals the root of the mass of oxygen, 32 grams per mole, over the mass of the unknown. Well, I'm in a little bit of a mess here, so I'm going to square the root to get rid of it. It's going to give me 0.126 equals the mass of oxygen over the mass of X, which is equal to 32 grams per mole over mx. The mass of X is equal to 254 grams per mole, so it's obviously one of the big gases. It says it's diatomic, so I'm just going to divide it by 2. It's 127 grams per mole per atom. And when we go to the periodic table and look at what that is, it must be iodine. That's how Graham's law works, or the rate of fusion. Finally, question 11, it's a real gas equation. So right before I even talk about this, I'm going to write out the more useful form of the real gas equation. So we did it in class, and it's quite convoluted, and there's P in a bunch of different spots. So when you rearrange it just to solve for P, you get this form. Again, this might be a good one to write down. It's also in your textbook, is where you probably would see it. It is a version of the van der Waals equation. So it just says the pressure is equal to these values, and we're going to of course use this table from your textbook to for your values of B and N. So we got a little bit of play to go here. So really quickly, I'm going to need a lot of space here. So pressure is equal to the number of moles. So right in the question, it's 1 atmosphere, 1 mole. So we're just going to start plugging numbers in. The ideal gas constant. Temperature is 0, so 273. Now I'm going to do the bottom. The volume is 22.41 liters. Take away 1 mole times B. So the gas we're dealing with is chlorine. We're going to get chlorine's values. So basically, at this point, it's just a matter of going through and trying not to do it all at once in your calculator, because that generally leads to mistakes. So you just start boiling it down, simplifying it. Trying to keep the units straight through the whole thing is can be challenging. Pressure is equal to 1.00268 atmospheres. Take away 0.0129 atmospheres. The liters would cancel here, doing atmospheres and atmospheres together. So using the real gas equation, I get 0.99 atmospheres, and the question has 1 atmosphere. So chlorine's going to behave essentially as an ideal gas at this value, and then it's only at incredibly small volumes or very low temperatures where we're really going to see any deviation.